All right. So, very last problem we did yesterday, there was a problem that was already in factored form for you. Two sets of parentheses multiplied together equals 0, and then we set both pieces equal to 0 and solve. What we're going to do today is figure out how to get it into that factored form, so then we can set the pieces equal to 0. Okay, so something like this is what we call a quadratic form. It looks like a quadratic. We've got a term that's squared, a term that's linear, not squared, and then a constant that's equal to 0. So this is something that's factorable. We're going to try in some of the other problems to factor it without substitution, but if you are having trouble with the cosines, you can think of it like this. Just put a y everywhere you see a cosine. We did a proof with something like this earlier. And then we're factoring. Now you could, if you want to, use like the box method, that sort of thing. If you're not comfortable with factoring, these problems are set up to be very small, easy numbers that you should really just be able to guess and check pretty quickly. So for example, what two things would you have to multiply together to get a 2y squared? 2 and 1y, right? So that's the only options you have for the front of each parentheses. What do you multiply together to get a negative 1 at the end? It's got to be a positive and a negative 1. So really the only part that's guess and check here is where does the plus go and where does the minus go. You want to place them so when you FOIL, multiply outside and inside, you get this middle term. So if I put a negative here and a positive here, my outside terms would be a negative 2y, my inside terms would be a positive 1y, and that would give me the negative 1y in the middle, okay? So, relating that back to my cosines now, I have factored it into 2 cosine x plus 1 and cosine x minus 1, which at any point here now you could FOIL it back out and make sure you're back where you started if you've done that correctly. So now we can use zero product property. Take each parentheses, set them equal to 0, like we did yesterday. Get the cosines by themselves. So here I'm going to have negative 1/2. And on this guy I'm going to have positive 1. And now we just locate the angles, and we are in radians here on our unit circle that will give us these values. So where on your unit circle in radians do you have a cosine that is negative 1/2? There should be 2 of them. 2 pi over 3 and 4 pi over 3. Where on your unit circle do you have a cosine of 1? It's 0, or you could say 2 pi. They're coterminal angles. So let's just say I put 0 there. Now the problem at the top says find all solutions, not just solutions between 0 and 2 pi. So what do I have to attach to the end of each of these? That plus 2 pi k. What's the only time you don't use a 2 pi? Tangent and cotangent. You would use what instead? Pi. Good. And of course, k is managed right there. It's just pi or pi k? It's going to be pi k. Okay, that's okay. Yeah, there's always a k there. Good? Make sense? Let's try this one. Okay, so two things that make this one a little yuckier. Number one, you have a sine and a cosine. They're not the same function here, so you are not even prepared to factor yet because of that. And there's that radical 3, but we'll mess with that later. We'll see what happens. Okay. You have to have all of the same function to be able to factor it. So we either need to make the sine squared into a cosine or the cosine into a sine. They both, one of them has to change to look like the other one. So what identities do you know that we could maybe replace something with something else that would be helpful here?
You could change sine over to 1 plus cosine squared.
Is that what you're saying?
No.
What was your huh?
Wait, never mind.
1 minus cosine squared.
Okay, so the Pythagorean identity is the one we're talking about, right? Some people will try to use like co-function identity here. I would not try to do that because that's going to change the angle. We don't want that angle to change in this problem. It's going to make it harder to solve. So sine squared, whatever one's squared, you can use Pythagorean identity. Remember your identity is 1 plus, or sine squared plus cosine squared equals 1. So sine squared is equal to what? 1 minus cosine squared. Okay, so now I have all cosines in the problem. And we have a little bit of simplifying first. So I'm going to distribute my 2 in. 2 minus 2 cosine squared plus rad 3 cosine plus 1. Combine my like terms. I have a positive 2 and a positive 1. So that will make it a positive 3 at the end. And then this is something we're going to factor. If I'm factoring, I don't like there to be a negative in that first term, so I'm going to divide everything by negative 1. I think that's going to make it easier. So it's going to be 2 cosine squared minus rad 3 cosine minus 3, and then 0 divided by negative 1 is still just 0 over there. Okay, so now we're in a place where we can factor it. I'm going to try to do it without the y's. What can you multiply together to get a 2 cosine squared? 2 and 1, and what is attached to those? Cosine. So again, not a whole lot of options here. Okay, what can I multiply together to get a negative 3? Yeah, so normally we do this with integers, right? A 1 and a 3, 1 positive, 1 negative, but that's not going to give me a rad 3. So the rad 3 in the middle is the clue here. Everybody agree rad 3 times rad 3 could also give me 3? 1 positive, 1 negative. So that's, again, the only kind of guess and check part is which one's positive, which one's negative. Remember, you want to be able to FOIL it so you can get that middle term when you put the outside and inside together. So this guy and this guy added together. If I put my negative here and my positive here, I'll have a negative 2 rad 3 and a 1 rad 3, which will give me a negative 1 rad 3 in the middle. Okay? And then again, you can FOIL it back out, double check that you've done that part correctly. Set both pieces equal to 0. If I set this guy equal to 0, I will get cosine x equals what? Negative rad 3 over 2. If I set cosine equal to 0, cosine minus rad 3 equal to 0, I will get cosine equals rad 3. Okay. And now I need to find those on my unit circle. 2 places where cosine equals negative rad 3 over 2. 5 pi over 6, and one more, 7 pi over 6. Where does cosine equal rad 3? Does that happen on your unit circle? No. So next question, is it possible for cosine equal rad 3? Because we saw ones yesterday like 0.7. 0.7 was possible, we solved it with our calculator. Is rad 3 possible? No, because it's bigger than 1. And think about your cosine and sine graphs. Those are only going to bounce between negative 1 and positive 1, right? So this is a value that cosine can never equal, which means I'm not going to get any answers from that chunk. Doesn't mean the whole thing has no solutions. It just means I'm not going to get any solutions from that piece. And this one just said all solutions on the interval 0 to 2 pi, so I don't have to worry about my plus 2 pi k's at the end here. 5 pi over 6 and 7 pi over 6 are the only 2 solutions. And then you can always plug them back in and make sure they work if you want. If the factoring gives you trouble, you could always, once you get to this point, use the quadratic formula. If I can spell that correctly, that would be amazing. I would say that this is probably a long way to do it, but if you get stuck, quadratic formula always works. Quadratic formula will spit out the 2 numbers that you set your cosine equal to. So it would spit out negative rad 3 over 2 and rad 3, and then you would just set cosine, whatever your trig function is, cosine in this place equal to 0, or equal to that, and then solve from there. Okay, but again, these should not be difficult factoring problems, so I would try to avoid that if you could. All right, can you try a couple? See how you can do? All right, try these 2. So again, we're finding just all solutions in the interval 0 to 2 pi, so you don't have to worry about your plus 2 pi k's, and we are in radians. So I'll give you a few minutes. All right, first one, just pi over 6 and 5 pi over 6. Good? Okay, yes, I can equal 2 there, bigger. All right, this guy, cosine squared. I'm going to replace it. All right. Same? Yeah. All right.
Isn't it
It's just 5 or 2.
Oh, thank you, thank you. I was looking at -1 for some reason when I did that. How'd you do? Questions? Okay, just got one more type of problem. This guy. One more type. This one we're going to do together and one you're going to practice on your own. 2 more problems. Okay. All right. So we have a Pythagorean identity, this guy, that relates cotangent and cosecant. The problem is that neither of these is squared to be able to replace one with the other one. So you have to square both sides to start. And we are allowed to do that because this is not a proof. I know I've said you're not allowed to do that a lot, but that's only in proofs. If it's an equation, that's fine. Okay? All right. Let's see. On the left side, I have addition inside that parentheses. So what am I going to do? You are going to FOIL. Okay, so let's do that first. First term, rad 3 cotangent times rad 3 cotangent.
3.
Gives me 3 cotangent squared. Outside and inside are going to be the same thing, so I'm going to have 2 of them. Rad 3 cotangent times 1 gives me rad 3 cotangent, plus another rad 3 cotangent is 2 rad 3 cotangent, and the last terms are going to give me just 1. On the right side, it's product, so you can just distribute the squared in. Rad 3 times rad 3, or rad 3 squared, is 3 cosecant squared. So what would you replace now using that Pythagorean identity? Yeah, this is a guy that sticks out. So let's replace him with 1 plus cotangent squared. What would you do next? Distribute. Okay. And now it's all the same function. This is definitely a quadratic. You can see the squared there. So in any good quadratic, we know the next step is get it equal to 0. When I try to get it equal to 0, if I subtract 3 cotangent on both sides, it's actually just going to cancel here. So you do not have to solve a quadratic. You can just get that one lonesome cotangent alone. Okay. Subtract 1. Divide by 2 rad 3, which the 2's will cancel, so you'll just have 1 over rad 3. And then that's what you're looking for on your unit circle now. How do you get cotangent with your unit circle? X over y. So x is going to have to be a half, y is going to have to be rad 3 over 2, and then they're both the same sign. So both positive or both negative is how we would get this. that happens in two places. 7 pi over 6, and there's another one, just pi over, oh wait, 7 pi over 6 isn't right. Pi over 3 is right, and then what's the other one? 4 pi over 3. Okay. We're not done though. When you square both sides of an equation, you could get extraneous solutions. What extraneous means you get it by solving correctly, but it doesn't work when you plug it back in. For example, here's a true or a false statement, right? But when I square both sides, it's now true. Okay? So it's only going to happen where you have negative values. So probably not anything in quadrant 1, probably something that evaluates like 4 pi over 3 is where I would check. Okay? So you can plug it back in. Let's say I want to check 4 pi over 3. These are values that you find on your unit circle. So I'm just going to use the original problem. Rad 3, cotangent 4 pi over 3, plus 1. I'm checking if it is equal to rad 3 cosecant of 4 pi over 3. What is the cotangent of 4 pi over 3? And hint, it's 1 over rad 3. Okay. What is the cosecant of 4 pi over 3? Cosecant is the reciprocal of sine. It's definitely negative because it's in quadrant 3. The sine is the y. So the sine is negative rad 3 over 2, which means the cosecant is 2 over rad 3. Over here, rad 3's cancel. I have 1 plus 1, which gives me 2. Over here, rad 3's cancel, negative 2. And this is exactly the kind of error you're going to see, because if I take that and I square both sides, I end up with this kind of false solution that 4 equals 4. So 4 pi over 3 is extraneous, meaning it's not actually a solution. The only solution to this guy is pi over 3. And if you plug pi over 3 back in, which you can, it'll check. But I would always start with the ones that would evaluate to a negative, because that's where the error occurs at. Okay? So these are the only problems that we have done where you could get extraneous solutions. Only when you square both sides you have to worry about it. All right. Last problem is yours to try. Square both sides to start. Let's see. If you're having trouble with the 4, because I think it gives you too many options, what could you do? Divide everything by 2. Reduce it. Good. Okay. And then 2 sine and sine. 1 and 1. And my plus has got to be here. My minus has got to be here. Sine equals -1. So we get, let's see, pi over 6, 5 pi over 6, 3 pi over 2. Good? Pi over 6 shouldn't give us any extraneous solutions. I think 3 pi over 2 will be good, because my cosine will be a 0 and my sine will be a -1, so you get 0 on both sides. 5 pi over 6 is the only one that I'd maybe check for extraneous. I don't know if it works or not. We're going to find out. Cosine of 5 pi over 6 is negative. Right 3 over 2. Sine is positive. Yeah. Oh, and then I get negative 3 over 2 and positive 3 over 2. The other two should work. Mm-hmm.
Could you just try and figure that, like, you have a sign change between, like, whatever project you're in with the angle you're given, like, with whatever, the sines or cosines that you have. Like, if they're conflicting, so one would be positive and one would be negative, and they're both supposed to be the same sign, you say that they're extraneous.
Not necessarily. That would be the case if it looks like this, where one's on either side. But like, what if it was sine plus cosine equals a number? Because then if they're opposite signs, it could work, right? And like 3 pi over 2 is 0 and -1. So I mean, those are probably the best ones to check first. That's what I do. But it could be other ones too, depending on the way it looks. So. I took this 3 sine squared, it was a negative, and I had to add it to the other side to get those terms together. So I have a 1 sine squared here, and I added 3 sine squared to it. Sine squared. And then this 3 I had to subtract from that 1 to move to the other side. So that -2 comes equal. How'd you do? Questions? That is it for 6-5. Okay. I have take-home quizzes for you. You do not need a graphing calculator for anything on here. Tests, I'm pretty sure you're going to have a red calculator. Use a graphing calculator, at least for the basic functions if you want. Tomorrow is a work day in here. Take-home quizzes are due on Monday. This one's not as long as your other ones have been, just because it's not over as much material. So hopefully that'll be a little bit nicer for you. Alright, so you have the last 2 minutes of the day to get started, all day tomorrow to work. Due on Monday, and then we'll start reviewing.